Section 4.7 in our textbook here discusses special segments in triangles, and we're going to be going through some of those special segments now. The first one is the median. The median of a triangle is just a segment drawn from the vertex of one angle to the midpoint of the opposite side. So if I take this triangle right here and I label the midpoint right here, and I connect the vertex opposite that midpoint to that spot, we've got a median of the triangle. It doesn't want to stay. And we can draw another one here. Now, of course, it doesn't have to be the bottom segment. We can connect the midpoint of one of the other sides to a vertex, and we can do that to all three. And that would look something like this if we did one for each triangle here. An altitude of a triangle is a segment drawn from the vertex of one angle, and it's perpendicular to the opposite side. So if I wanted to draw an altitude from this vertex right here to the opposite side, I just make sure I have to hit the opposite side at a right angle. Now I could draw one from this one to this side. I just have to make sure I hit, I just make sure I have to hit the opposite side at a right angle, like so. So what that would look like, we could draw one here, one here, one here. And if you notice here on a right triangle, one of the legs can be an altitude because we're talking about how tall it is from the base to the top. Now with this obtuse triangle, we could still draw one from this vertex to this side by extending the side and then drawing the vertex straight down. Which is a little bit trickier. We just remember to have a right angle, we have to draw it to the opposite side. So we're allowed to extend these sides for the altitude. And just remember the altitude is if it were the side with the right angle, if that was at the bottom, you'd be climbing to the very top. You want to know how exactly how tall that triangle is. All right, a perpendicular bisector. Now this isn't something that has to be drawn for a triangle. Now we're going to be talking about what happens when we draw the perpendicular bisectors in triangles, but a perpendicular bisector is drawn on a segment. And it's exactly what the name says. It's perpendicular to that segment, and it splits that segment in half. So if I'm looking at this segment here, I need to label the midpoint, because a bisector has to go through the midpoint, and I have to draw a line that's perpendicular, like so. And if I wanted one that was drawn really well, it would look like this. Okay? And we would have a right angle, and it's on the midpoint. And you can do that to the segments of a triangle. You can draw a perpendicular bisector. I've drawn one for this triangle, one for this triangle, one for this triangle. Now, of course, I could draw a perpendicular bisector for all three segments of the triangle, which you could do. All right, and at this point, I can pause this video and try page 155, numbers 1 through 3, to test your knowledge on medians, altitudes, and perpendicular bisectors. Okay, each triangle can have 3 of the special segments drawn to it. So if I draw all 3 medians of a triangle, it would look something like this. And what we notice is they all happen to land at a single point. And I can draw all 3 altitudes. Notice I went to a right angle on each of these sides, right angles. Okay. And I can do a perpendicular bisector for each segment. Now the perpendicular bisector does not have to connect to one of the vertices. It just has to be perpendicular to each segment. So, for example, this line right here is perpendicular to this side of the triangle at its midpoint. Okay. All right, theorem 4.5 and 4.6, these are converses of each other. We've just combined the two statements in a biconditional by saying if and only if. And we say a point is equidistant from the endpoints of a segment if and only if it lies on the perpendicular bisector of that segment. And what that means is if I have this point and I say it lies on the perpendicular bisector, which I'll draw right here. If this yellow line is the perpendicular bisector of this segment, it's the same distance from this endpoint as it is from this endpoint. And we could prove this using the two congruent triangles here that are congruent, because remember this was a midpoint. So if we're on the perpendicular bisector, we have two congruent triangles by side angle side. So that means this length would have to be equal to this length. And conversely, if those lengths were equal, you would know that this would have to lie on the perpendicular bisector. And at this time, you should pause the video and try problems 4 through 6 on page 155 with these classroom exercises. Okay, distance. The distance from a point to a line is defined as the length of the perpendicular segment from the point to the line. So if I'm looking at this point here and this line here, this is the distance from the point to the line. You wouldn't want to measure the distance from a point to a line and say, all right, this right here represents the distance. It's 15 centimeters from this point to this line because there's a shorter distance right here. So we got to use the shortest distance, which is a perpendicular. Theorem 4.7 and 4.8. Again, we're combining two theorems that are converses of each other with a biconditional. And they say that a point is equidistant from the sides of an angle if and only if the point lies on the bisector of the angle. So we're saying that if we have a point that's equidistant from the two sides, remember the distance from a point to a line is a perpendicular segment, so these would have to be right angles here. Then that means the bisector is going to go through that point, the bisector of this angle. And at this time, you should try problems 8 through 10 on page 155. And that's the end.